A single random event is pure chaos. You flip a coin, and while it's in the air, the outcome is completely unknowable. Yet, if individual events are impossible to predict, we have somehow built massive, highly stable industries that rely entirely on these exact same random outcomes. Consider a casino. A roulette wheel is just a physics-based random number generator, but those alternating red and black slots reliably produce billions of dollars in guaranteed annual profit. Or look at political polling. Statisticians watch a few thousand people drop a single ballot into a box, and from that tiny random sample, they accurately project the behavior of hundreds of millions of voters. In advanced manufacturing, teams handle millions of individual components across highly complex supply chains, while mathematically guaranteeing fewer than 4 defects per million parts. This presents a bizarre mathematical paradox. If every single coin flip, individual vote, or microscopic factory error is inherently chaotic, how do these massive systems capture that unpredictability and turn it into absolute certainty? The answer relies on 2 mathematical pillars. The first is a principle called the law of large numbers. This chart tracks the average result of flipping a coin. If you flip it just 10 times, the proportion of heads is extremely volatile. The average will swing wildly away from the true 50% mark because a small sample size is dominated by random noise. But watch what happens as we scale up to 10,000 flips. The line flattens out and locks perfectly onto that 50% true mean. The law of large numbers dictates that as sample size grows, random variations automatically cancel each other out, revealing the underlying truth. There is a practical problem, though. In real life, we rarely have the time or money to gather tens of thousands of data points. We are usually forced to make decisions based on much smaller samples. The law of large numbers guarantees we will eventually find the true average if we scale to infinity, but it leaves us blind to how much error exists in the smaller samples we use. It doesn't tell us what the error looks like. This is a distribution graph showing a dataset with a heavy right skew. The data here is lopsided, chaotic, and completely non-symmetrical. If we pull a small random sample and calculate its average, we plot that result as a single dot on a new axis below. We repeat this process thousands of times, generating new averages and stacking them up. Something remarkable happens. No matter how wildly skewed the original data was, the distribution of these new sample averages always forms a perfectly smooth symmetrical bell curve. This is the Central Limit Theorem, the second pillar of statistical certainty. It proves that the random errors in our samples always arrange themselves into a highly predictable shape. We can even quantify exactly how fast this shape materializes. A mathematical formula known as the Berry-Essend theorem calculates the optimal rate at which this normal curve forms as we add more data. Because of this theorem, we know exactly when a finite, realistic sample size is large enough to rely on. We don't need infinite data to find order, because a predictable shape of error is forced into existence very early on. Knowing that sample averages always form this normal distribution gives statisticians an incredibly powerful tool. Because the shape of the error is always the same, we can apply a single set of standardized mathematical rules to almost any system. This chart illustrates normal distribution. Because of its strict geometry, exactly 95% of sample averages fall within 2 standard deviations. This bracket is how political polling works. A margin of error simply applies this boundary to survey data. Manufacturing teams use this exact same geometry. By calculating how many standard deviations, or z-scores, a sample is from the target dimension, they can strictly control the quality of an entire production line without needing to inspect every individual part. A pharmaceutical facility can test a handful of tablets from the batch, measure the variance, and use the Central Limit Theorem to mathematically guarantee the dosage safety of the entire mountain of pills flowing through the machinery. When we look at a single isolated event, randomness looks like a fog that obscures the truth. But once you scale it up, that same unpredictability becomes the mathematical engine that generates perfect, reliable order.